Okay, now looking at exponential growth and decay. So our exponential growth and decay model is this exponential model here, A of t. So A of t represents the amount present after time t. So t representing our time variable, whatever that may be, whether it be days, years, months, that'll be t. And A being the amount present, again, after this amount t, time t. Now A sub 0 would be the initial amount. So what we started with initially at time t equals 0. And times e, so it's a natural exponential model like we have with our compound interest continuously model, raised to a power of k times t. Now k represents your rate. So we have a growth rate if k is positive. We have a decay rate if k is a negative number. So let's take a look at the example down here, number 5. It says the size A of a certain insect population at time t in days. So t is represented in days, so our time value. Obeys the following model, A of t, so amount present after t days, equal to 500. So here's your initial amount. There's A sub 0, times e to the 0.02. 0.02 is our value of k, and it's positive, so we're looking at, again, a growth model, times t. It says here in part A, determine the number of insects at time t equals 0. Well, at time t equals 0, that should be our initial amount, right? That should equal A sub 0, right? So that should equal 500. So let's show that algebraically. So A of t would be A of 0 equal to 500 times e to the 0.02 times 0. As we multiply 0.02 times 0, we know we get 0. And we know that e raised to a power of 0 simplifies to 1. So we end up with 500 times 1, or 500 insects. So yeah, there's our initial amount. That was A sub 0. Part B said, what's the growth rate? Well, we know k in this example was 0.02. So that equals, as a percentage, 2%, right? 0.02 times 100. So move our decimal 2 to the right to convert the decimal to a percentage. But there's our growth rate for this insect population. What is the population after 10 days? So after 10 days, so t is 10. So we want to look at the amount of insects in 10 days. A of 10 equal 500 times e to the 0.02 times 10. So let's go ahead and see what that is. We'll put it in on our calculator. All right, let's go ahead and type that in together. So we got 500 times e, so second ln, there's our e, 0.02 times 10. So 610.7. So 600, what? Approximately 611, round to the nearest insect. So 611 insects. So after 10 days. When will the population reach 800? So our question is, when does A of t, the amount present after t days, when will it be 800? So with that said, we go to our model. 800 needs to equal 500 times e to the 0.02 times t. So again, we're solving for t. So to solve for t, let's go ahead and divide out the 500 on both sides. As we do that, that simplifies down to 8/5 equal to e to the 0.02 t. Now, with that, we got an exponential equation, right? We got to solve for t up here in the exponent. Now, if we could get the same base, we would do that. We can drop down the powers. But since we can't, we can always introduce logarithms. So since it's dealing with our natural number, let's go ahead and look at the natural log, right, of both sides. So let's take the natural log of 8/5, and it equals the natural log of e to the 0.02 t. And again, the reason I did natural log, here's our same base property. We know natural log of e to 0.02 t is 0.02 t. So remember our property, right? Log base a of a to the x always simplifies to x. So we end up with a natural log of 8/5 equal to 0.02 t, and as we divide out 0.02 on both sides, we'll have our answer. So natural log of 8/5 divided by 0.02. So let's find out what that gives us. So we'll put that in here. So what's the natural log of 8/5? All right, divided by 2. So I got 0.235, right? I'm plugging that in, natural log of 8/5. Now let's make sure we type that in correctly, right? What we trying to type in, I put 0.2. It was 0.02, wasn't it? So let's go type that in correctly. I knew that answer didn't make sense, so we need to make sure we double check what we're typing in to divide by 0.02. That makes sense. So we got 23.5. So there's the amount of time, and remember t is in days. So 23.5 days. So there's our amount of time there it'll take to reach a population of 800 insects based off that 2% growth rate. All right, looking at our last question, when will the insect population double? So when will we double our initial amount? So when will A of t equal 2 times the initial, right? Or 2 times, we'll not stick to our initial amount, A sub 0. So when will that equal 2 times what? 500. When will it equal 1,000? So with that, let's go ahead and set that up. So in our model, when will 1,000 equal 500, all right, times E to the 0.02 t. So we solve this equation. So we divide out 500 on both sides to isolate, right, the exponential term. Right, 2 equal e to 0.02 t. We know with that we need to take the natural log, right, of both sides, so we can bring down t and solve for it. So since we're dealing with our natural number, we make this a lot easier by doing natural logarithms. So the natural log of 2 equal to the natural log of e to the 0.02 t. Well, again, that simplifies nicely. Using our same base rule, that equals 0.02 t. So we have the natural log of 2 equal to 0.02 t, and we divide out 0.02 on both sides. Right? What does t equal? Natural log of 2 divided by 0.02. So let's go see what we come up with. What is the natural log of 2? Right? Divided by 0.02. 34.65, right? 34.65. Right? 34.7 days to double our initial investment. So again, it took 26 days, or 24 days, I should say, to get 800. To get the 1,000, it's going to take 34.7 days, which are double our initial population. All right, let's move on here to example 5. We've got another exponential problem here. Now this is same problem. Let's do a new one. Going on here, problem number 6. So number 6, it says here iodine-131 is a radioactive material that decays exponentially over time in days. Suppose that 100 grams are present initially. After 9 days, 45 grams are left. All right, so that's what's left after 9 days. So remember, this is decaying exponentially. And again, our decay rates, what we're going to be looking for is we want to find K. Now, one thing we know about K will be negative as it decays exponentially. We know that our initial amount, A sub 0, equals 100. Right, we had 100 grams present initially. And after 9 days, we know A of 9, it equaled 45 grams. So let's use that information, right, for this iodine-131 radioactive material. Let's use that to solve this one. So remember our model, A of t equals A sub 0, the initial amount, times e to the kt power. So with that, we got A of t. So we want to look at this problem here. We got 45 grams equal to our initial 100 grams times e to the k, which we don't know, times t. Well, t is 9 times 9. So I've got 45 equal to 100 e to the 9k power. So we've set up our exponential equation here to go solve. So we're going to solve that. Of course, we know we need to isolate. So we'll go ahead and divide out 100 on both sides, right, to get it by itself. So we've got 45 hundredths equal to e to the 9k power. And then we'll take the natural log of both sides, right? So we can solve the exponential. We're going to take natural log. So natural log of 45 hundredths. Okay, equals, let's go do the same thing over here. Let's take the natural log of the right side. And this is the reason we did natural log, right? So we can use our same base rule. We know all of that equals, that simplifies to 9k. Same bases that wash out. So we end up with a natural log of 45 hundredths equal to 9k. And then as we divide out 9 on both sides, we'll have our answer. So k is a natural log of 45 hundredths divided by 9. So let's see what we get. And we should get, again, a negative value, right? Since this is a decay problem. So let's go plug that in together so we can clear out our last one. So we got natural log of 45 hundredths divided by 9. So I got negative 0.088. Negative 0.088. Right? And again, I'm going to the nearest thousandth. So if you want, it'll be 0.089, wouldn't it? So let's go ahead and take that to the nearest thousandth. Now again, that's a rate. So as we change that to a rate, that's negative what? We move our decimal to the right. Negative 8.9%. So what's our decay rate? Our decay rate is negative 8.9%. So again, we're finding that amount again after 9 days is decaying at a rate of 8.9%. What is the exponential decay function? So let's go ahead and write the model. A of t equal to our initial amount, 100, times e to the k. Let's go ahead and write it in here as a decimal. Negative 0.089 times t. So there's our exponential decay model. How much iodine 131 is left after 2 days? So here t equal 2. So we want to know the amount after 2 days. That'll be A of 2 equal to 100 times e to negative 0.089 times 2. All right, so let's go plug that in and see what we come up with. So on our calculator, let's get our TI back out. So here we got 100 times E, so second ln, E to the negative 0.089, 8.9% decay rate, times 2, right? 2 days. So as we put that in, I got 83.69. 83.69. Right, or approximately what? 84 grams. We're going to round it to the nearest gram. So after 2 days, there's 84 grams. Of course, we know after 9 days it's 45 grams. But again, this is decaying at a rate of what? 8.9%. All right, let's go to looking at our value here. Let's go to D. When will 1 gram of iodine 131 be left? So when will A of t equal 1? That's our question. So let's set that up. So when will 1 equal initial amount 100 times e to the negative 0.089 t. So as we're solving this exponential equation, let's go ahead and divide out 100 on both sides. So we do that, we got 1/100th equal to e to negative 0.089 t. And we know now we're ready to take the natural log of both sides. as we're going to solve this equation. So as we do the natural log of the left side, natural log of 100th equal to the natural log of the right side. So we got the natural log of e to the negative 0.089t. And again, we did natural logs, the same base rules. So we got natural log of 100th equal to, we know all of this simplifies to negative 0.089t. So negative 0.089t. As we divide out negative 0.089 on both sides, we'll have our answer. So t equals the natural log of 100 divided by negative 0.089. All right, so let's go type that in. Let's see what we come up with. Let's put that in our calculator. So we got natural log of 100th, 1 divided by 100, divided by negative 0.089. So I got 51.7. 51.7. So that's what? Approximately 52 days. So it'd take around 52 days to get down to just 1 gram left. What is the half-life of iodine-131? So what is half-life? That will be when our amount is half of what we originally started with. 1/2 of our initial, 1/2 of A sub 0. Right? So when will it equal 1/2 of 100? When will it equal 50 grams? So that's half of our initial. So let's find out. So we'll set it up. So 50 equals 100 times e to negative 0.089 t. And let's go ahead and take our equation. Let's solve it. Let's go ahead and isolate. So as we reduce 50 over 100, of course, is 1/2. We got 1/2 equal to e to negative 0.089 t. And now let's go ahead and take the natural log of both sides. So we'll take the natural log of 1/2, right, equal to the natural log of the right side. Natural log of e to the negative 0.089 t. And again, that simplifies to negative 0.089 t. So we end up with natural log of half equal to negative 0.089 t, and then divide out our coefficient. And we'll have our answer. We'll have the half-life of iodine, 131. So what do we get? What's ln of 1/2 divided by negative 0.09? So ln of 1/2, and type that in correctly. All right, divided by negative 0.089. So half-life is 7.7. So 7.7, we got t. So t is approximately what? 8 days. Right? So half-life, 8 days. So get half the initial amount, take 8 days to get to 50. 9 days is 45. Right, as you can see in our different problems we worked through. But that's, again, some examples of exponential growth and decay. So again, as we're looking back through this one, so we found our decay rate, 8.9%. Again, our K value is a negative value, decaying at a rate of 8.9%. So again, K value giving us that rate, an example we're dealing with. So again, I hope that helps with your exponential model. So some good applications to look at.